Ever get that feeling like you want to understand something complex, but without like getting stuck in a million details, you know? I think we all do. And that's kind of what we try to do here on the deep dive, right? Today, we're diving into a topic that might seem a little intimidating at first, but bear with us, because it's way more useful and even kind of elegant than it might seem at first glance.
You hit the nail on the head. It's all about those moments where you suddenly see the underlying structure, right? Those aha moments. And today we're going to experience one of those with a concept called the binomial theorem.
The binomial theorem. Yeah, it does sound a little bit like a mouthful, right? Like back to high school math class. But think about it this way. How would you even begin to calculate something like 98 to the power of 5? Or like a 101 to the power of 6? Can you imagine multiplying all that out by hand? Oof, it would take forever, and I would definitely mess it up.
It would be a nightmare. And that's exactly the challenge our source material for today starts with. We're looking at some really fascinating excerpts from a math textbook, and they point out this exact problem. They say that the binomial theorem is like a shortcut.
A shortcut. I like the sound of that. So where do we even start with this binomial theorem thing?
Well, the textbook starts with the basics. Good old binomial expansions. We're talking about a plus b raised to different powers, starting with 0, then 1, then 2, 3, and 4. They show you what each of those looks like when you expand it.
Okay, so like a plus b squared is a squared plus 2ab plus b squared, that kind of thing.
Exactly. They lay it all out like that. And as you look at these expansions, some really interesting patterns start to emerge. Did you notice any just from glancing at them?
Let me see. Well, it seems like the number of terms in the expansion is always one more than the power. Like a plus b squared has 3 terms, is that what you mean?
You got it. That's the first pattern. What else do you see? Look at the powers of a and b in each term.
Oh yeah, the powers of a start high and then decrease by 1 in each term until it's gone. And the powers of b do the opposite. They start at 0 and go up by 1 in each term. It's like a mirror image almost.
Exactly. And there's another cool pattern. If you look at any single term in the expansion and you add up the power of A and the power of B, what do you get?
Let me see. Oh, wow. It's always equal to the original power we started with. Like in a plus b cubed, every term's powers add up to 3. That's really neat.
It is, isn't it? And the textbook then introduces this visual tool for organizing all these patterns, Pascal's triangle. Have you heard of it?
Vaguely, it's a triangle of numbers, right? It's something about adding the numbers above to get the one below.
That's it. You start with a 1 at the top, and then each row below starts and ends with a 1. The numbers in between are the sum of the two numbers directly above them. The textbook actually shows some diagrams of it, which is helpful.
Right, right. I'm picturing it now. And so how does Pascal's triangle connect to these binomial expansions?
The numbers in each row of Pascal's triangle are the coefficients of the terms in the binomial expansion. Like if you want to expand 2x plus 3y to the fifth power, you'd look at the fifth row of Pascal's triangle.
May guess. The fifth row starts with 1, 5, 10, 10, 5,
You
1.
got it. And those become the coefficients in the expansion. You'd have 1 times 2x to the fifth plus 5 times 2x to the fourth times 3y and so on. It's a really clever way to avoid doing all that manual multiplication.
That's pretty cool.
That-
But I can see how it could get a little cumbersome. Like if I wanted to expand something with a really high power, like 12, I'd have to write out 12 rows of Pascal's triangle.
You're right. And the textbook brings up that exact point. They ask if there's a more direct way, a faster way, especially for those higher powers.
I'm all ears. What's this faster way?
It involves combinations. Remember those? That in choose R thing, written as NCR.
Yeah, kind of. It's about figuring out how many different ways you can choose R items from a set of N items. But I don't quite see how that connects to this.
Well, the textbook shows how you can actually rewrite Pascal's triangle using combinations instead of just the numbers. Like instead of the number 5 in that row we were looking at before, you'd have 5c1.
Okay, I'm starting to see a connection here. So instead of building the whole triangle to find the coefficient, I could just use this NCR formula.
Exactly. It's a more direct approach. It lets you calculate any specific coefficient in the expansion without needing all the previous rows.
So is this where the actual binomial theorem comes in, like the formal statement of it?
This is it. The textbook gives us the full formula. For any positive whole number n, a plus b to the power of n equals a sum of terms. It goes like this. You have NC0 times a to the n plus NC1 times a to the n minus 1 times b plus NC2 times a to the n minus 2 times b squared. And you keep going until you get to NCn times b to the n.
Wow, okay. It's a bit of a mouthful, but I can see how it matches up with the patterns we were talking about earlier.
Yeah.
The NCR part is the coefficient. The A powers are decreasing. The B powers are increasing. It's all there.
It really is all there, and the textbook doesn't stop there. They even give a little intro to how you can prove the binomial theorem using something called mathematical induction. Have you ever used that?
I remember hearing about it, but I don't think I could explain it. What's the basic idea?
It's like a domino effect. You first prove that the theorem works for the very first case, usually when n equals 1. That's usually pretty simple.
Okay, and then what?
Well, then you assume that the theorem is true for some arbitrary number, k. And then you use that assumption to prove that it must also be true for k plus 1, the next number up.
So it's like if the first domino falls and we can prove that any falling domino knocks over the next one, then all the dominoes must fall. Sure.
Precisely. And the textbook even mentions a specific identity involving combinations that's crucial in this proof. KCR plus KCR1 equals K plus 1 CR. It basically connects the coefficients in one row of Pascal's triangle to the coefficients in the row below it. But I think we can move on from the proof for now, unless you want to dive in further.
Yeah, maybe another time. So we've got the formal theorem now. But does the textbook give us any examples of how to actually use it?
Oh, absolutely. They've got a whole bunch of examples. For instance, they show how to expand x plus 2 to the sixth power. They go through each term step by step, calculating the coefficients and the powers.
And it really works. You get the same answer as if you had multiplied everything out by hand.
It really does. And they also point out some key observations in terminology, like those NCR values we've been talking about. They're officially called binomial coefficients. And they remind us that an expansion of a plus b to the n always has n plus 1 terms. The a powers descend, the b powers ascend, and their powers in each term always add up to n. All the patterns we saw, they're all consistent.
Okay, so far so good. What else is there?
Well, then the textbook gets into some special cases, like what happens when you have xy to the n instead of x plus y to the n. Do you see what changes?
Well, instead of adding y, we're subtracting it. So instead of plus signs in between all the terms, would some of them be minus signs?
You got it. The terms alternate between positive and negative because you're raising a negative number to different powers. They show this with an example like x2y to the fifth.
Okay, that makes sense. And then there's that special case where you have 1 plus x to the n. That seems like it would simplify things a lot.
It does. If a is 1, then 1 to any power is still just 1. So you end up with a simpler formula, nc0 plus nc1 times x plus nc2 times x squared, and so on. And this simplified version is super useful for all sorts of things, like approximations and deriving other math formulas.
Oh yeah, like what?
Well, the textbook shows you what happens if you substitute x equals 1 into that 1 plus x to the n expansion. You end up with this neat little equation. 2 to the power of n is equal to the sum of all the binomial coefficients for that n.
Wow, that's pretty cool. So if you add up all the numbers in a row of Pascal's triangle, you get 2 to the power of whatever row number it is.
Exactly. And there's a similar result if you substitute x equals 1 into the expansion of 1x to the n. You get 0 equals nc0 minus nc1 plus nc2, and so on, alternating signs until the last term.
So the sum of the coefficients with alternating signs is 0.
That's interesting. I'm starting to see how this seemingly simple theorem has a lot of depth to it.
Absolutely. And now the fun part. The textbook shows us how to actually use the binomial theorem in real-world scenarios with a whole bunch of practical examples.
Laid on me, what kind of examples?
Well, they start with one that looks a bit more complicated. Expanding x squared plus 3 over x to the fourth power.
So instead of just a and b, we've got these bigger expressions. Does the theorem still work?
It totally does. You just treat those bigger expressions as single units and apply the powers and coefficients the same way. The example shows you all the steps, and it might look a little messy, but it all works out in the end.
Yeah, okay, I'm kind of following. What's the next example?
This one is super practical. Remember how we talked about how awful it would be to calculate 98 to the fifth power by hand? Well, guess what? The binomial theorem can help us with that.
I'm intrigued. How does it help?
Yeah.
They show how to rewrite 98 as 100 to 2 and then raise that to the fifth power. Now, powers of 100 are super easy to calculate, right?
Oh, I get it. And then we can use the binomial theorem to expand the whole thing.
Wait.
Way easier than multiplying 98 by itself 5 times.
Exactly. They even do the full calculation in the example, so you can see how much easier it is.
That's a great trick. What else?
Well, there's this really interesting example where they compare 1.01 to the 1 millionth power with 10,000.
Whoa, that's a huge power. How do you even begin to compare those?
That's the point. It seems impossible to calculate directly, but they use the binomial theorem to approximate the first few terms of 1 plus 0, 1 to the million. It ends up being 1 plus 10,000 plus some other positive values.
So just by looking at the first few terms, we already know that 1.01 to the million is way bigger than 10,000. That's some powerful approximation.
It really is. It shows how even small increases, when compounded over and over again, can lead to enormous growth. Think about how that applies to things like interest in finance or population growth.
Okay, I'm starting to see the power of this theorem. What was the last practical example?
The last one is about proving something. They show how to prove that 6 to the n minus 5 to the n always leaves a remainder of 1 when you divide it by 25.
That sounds kind of abstract. How does the binomial theorem help with that?
They rewrite 6 to the n as 1 plus 5 to the n, and then they use the binomial theorem to expand it. They point out that all the terms except the first two have 25 as a factor because they have 5 squared in them.
So you can rewrite the whole thing as 25 times some number plus 1, which means it always leaves a remainder of 1 when divided by 25. That's really clever.
It is, right. So we've seen how the binomial theorem helps us expand things, calculate things, approximate things, and even prove things.
Okay, I'm sold. But where do we go from here? Is there more to this theorem?
There's a lot more. The textbook then goes into detail about the general term of a binomial expansion and how to find the middle term or terms.
The general term. What's that?
It's basically a formula for any specific term in the expansion. It tells you the coefficient and the powers of a and b for the r plus 1th term.
Ah, so like if I want the fifth term, I can just plug in r equals 4 and get the answer directly without needing all the previous terms.
Exactly. And then there's the middle term, or terms. If the power n is even, there's only one middle term. But if n is odd, there are two middle terms.
Okay, how do I know which term is the middle one?
They give you formulas for that too. If n is even, the middle term is the n2 plus 1th term. And if n is odd, the middle terms are the n plus 1 2th and n plus 1 2 plus 1th terms.
I'm writing all this down. What else?
Well, they also talk about something called the term independent of x. It's a term that has no x in it, just a constant number. They show you how to find it in expansions like x plus 1x to the 2n.
That seems useful. How do you find it?
It's the term where the powers of x from the x and the 1x cancel each other out. They show you how to figure out which term that is.
Okay, I'm seeing a pattern here. The binomial theorem gives you a way to find any term you want without expanding the whole thing.
You got it. And they give a bunch of examples to show you how to do this, like finding a if the 17th and 18th terms of 2 plus a to the 50 are equal.
So you use the general term formula and solve for a. Got it. What other examples are there?
They derive a formula for the middle term in 1 plus x to the 2n. They show how to find the coefficient of x to the 6th times y cubed in x plus 2y to the 9th. They even show you how to work backwards sometimes. Like if they give you the second, third, and fourth terms of an expansion, can you figure out what x, a, and n are?
That's like a puzzle. Use the terms to figure out the original expression.
Exactly. It's all about using the theorem to solve different kinds of problems. And then they revisit the term independent of x, but this time with more complicated examples involving fractional exponents.
Fractional exponents, like x to the 23.
Yep. It's the same idea, but the algebra gets a bit trickier. You still need to find the term where the power of x is 0, but you're dealing with fractions now.
Okay, and what about those miscellaneous examples the textbook mentioned? Are those even harder?
They are a bit more advanced. They show you how to prove relationships between n and r when coefficients are in arithmetic progression. They connect the middle term of one expansion to the sum of the middle terms of another expansion. They even show you how to find coefficients in the product of two different binomial expansions. It gets pretty wild.
So we're talking about using the binomial theorem to prove things, connect things, find things. It's a lot more than just expanding stuff.
It really is. And they even mention a bunch of topics they cover in the miscellaneous exercise section. Things like proving divisibility rules, expanding trinomials, and even using the binomial theorem for sophisticated approximations.
So, like, we've only just scratched the surface here.
It feels that way, doesn't it? The binomial theorem is this foundational concept that shows up everywhere. It's like the secret weapon mathematicians use to solve all sorts of problems.
So to wrap things up, what would you say is the main takeaway from all this?
I'd say the binomial theorem is this incredibly powerful tool for expanding expressions of the form a plus b to the n. It gives us a shortcut, a systematic way to avoid all that tedious multiplication. And it's based on these things called binomial coefficients, which we can find using Pascal's triangle or that NCR formula.
And it's not just about expanding stuff. We saw how it helps us calculate things, approximate things, and even prove things. It's like this Swiss Army knife for math
It
problems.
really is. It's a beautiful example of how an abstract math concept can be super practical and useful.
So as we end our deep dive today, I want to leave you with this thought. Math is all around us, even if we don't always see it. The binomial theorem is just one example of how a seemingly simple idea can have a huge impact on how we understand and solve problems. Who knows what other hidden math structures are out there waiting to be discovered? That's something to ponder, isn't it? Thanks for joining us.